Okay, so we're going to go through the work for exercise 9c of the Pearson Applied 1 textbook. So this is about SUVAT equations. It's the first exercise on SUVAT equations. So first we're going to talk about what SUVAT is. We're going to derive two of the equations and then use them. So first of all, S is the displacement, U is the initial velocity, V is the final velocity, A is the acceleration, and T is time. So we're going to start off with some known facts. So we're going to start off with acceleration is equal to change in velocity over time. Obviously acceleration is A, change in velocity is the final velocity minus the starting velocity, and T is time. Now there we have a formula connecting those four variables, but when you're asked to derive them in an exam, you'll be asked to put it into the more common form. Just using some simple algebra, we get V equals U plus AT. And then the next one we're going to derive, if you know that the distance travelled is average speed times time, so in vector form that's displacement is equal to the average velocity, so U plus V over 2 multiplied by time. And that's the second one we're going to use. So now if we apply those two SUVAT equations, first of all, a cyclist is travelling on a straight road, accelerates from 4 meters per second to 7.5 meters per second in 40 seconds. And we want to find the distance travelled over those 40 seconds and the acceleration over those 40 seconds. So the first thing we're going to do is draw a diagram. And in this case, we don't want to be trying to draw any bikes or anything. It's just two particles showing the initial and final velocity. And then write out all the letters of SUVAT, fill in the bits you know and what we're trying to find. Okay, so now if we're trying to find the distance travelled, so we're trying to find S, we want to use the second SUVAT equation we've got. So we're going to use S, U, V and T. So if we write out the equation, sub in your values, then you can simply calculate S, which is 230 meters. That's actually the displacement, not the distance travelled, but in this case it's accelerating, so it's not going to be doubling back. We'll look at an example where that's more complicated later on. And then to find the acceleration, obviously we're going to use the other SUVAT equation for the acceleration. We can put in the value of S we've got now, which is 230, although we're not going to use it at the moment. So we find the acceleration, we've got these four values, so we're going to use the first equation, sub them in, sub the values you know in, rearrange it, and you should get A is 0.0875 meters per second squared. Okay, looking at another example now. A particle moves in a straight line from A to B with constant deceleration of 1.5 meters per second squared. The speed of the particle at A is 8 meters per second, at B it's 2 meters per second, and we want to find the time taken to get from A to B, the distance from A to B. Okay, so first of all we'll draw a diagram. Again, just two particles representing the initial and the final positions and speeds. Write out SUVAT with all the values we've got and what we're trying to find. Remembering that A is negative because it's a deceleration, not an acceleration. So we're trying to find the time first of all. So here we're going to use the first formula we've got. We'll sub the values in that we know. And then solve that. And we get T equals 4. Okay, so we can put that in where we had T. And then move on to part B. So this time we're trying to find the distance from A to B. So we're trying to find S, we've got U, we've got V, and we've got T. We know it took 4 seconds to get there. So write out your formula, sub in the values you've got, and you work out that S is 20 meters. Okay, so that was a fairly straightforward example because it's just moving from A to B. What we're going to do now is move on to sort of slightly complicate things. So after reaching B, the particle continues to move along the straight line with the same deceleration. The particle is at point C 6 seconds after passing through A. And this time we're trying to find the velocity of the particle when it's at point C. So first of all, we'll update our diagram. Okay, to show point C here. And we know it reaches that point 6 seconds later. So we're going to find the velocity at C and also the distance from A to C. So before we can write out our SUVAT values, we need to think about our journey and where our journey starts and ends. So you could work out the velocity at C, go from B to C. However, the next part of the question wants the distance from A to C, so it makes sense to say our journey goes from A to C. So So the initial velocity will be 8. So we're going to say our journey goes from A to C. So put in the values we've got. And we're trying to work out V. So we're going to use the first SUVAT equation. We're going to sub in our values. And then work out that V equals -1 meters per second. Right, the interesting thing about that, obviously, it's a negative velocity, which means that it's going to the left. Okay, which clearly means that before 6 seconds, it was going away. So there was a point when it went through C with a positive velocity, which would have been 1. Okay, so we're going to consider that when we move on to part B. So for part B, so we can now put in our velocity. We know it's -1 when we get to C, and this time we're trying to find S. Sometimes I'd warn against using a value that you've just found in a subsequent calculation, but in this case it was an exact value, we didn't have to round it. But if you rounded it, try to avoid using those values. So we want to use our second SUVAT equation. So we sub in the values we've got, we're trying to find S, and we get 21 meters as the distance from A to C. Now, the important thing to remember is that that's a displacement. Okay, so it's the distance from A to C. It's not the same as the distance travelled by the particle, because it went past C and then came back. So you need to be careful about the wording in the questions when you're answering these kinds of questions.